An exponential function is a function that either looks like a constant raised to a power, like 10 to the power x, that's a constant raised to a variable power. Or it looks like anything in the location scale family of that. So like this function g is the same thing as 2 raised to the power x, but it's moved 1 unit to the left and 3 units down, so I'd say it's in the location scale family. And so these are all things that we call exponential functions. The biggest point, I guess, of confusion for a lot of people is the difference between this and this. If the variable is in the base and your exponent is a constant, that's just a polynomial, right? Or if the exponent is something weird, maybe we call this a power function. Because it's x raised to some weird power. But if it's x raised to integer, or maybe I shouldn't say integer, if it's x raised to a natural number or a positive integer, we call that a polynomial. And then if we flip the script and we say, okay, the base is now the constant and the exponent is now the variable, that's what we call an exponential function. Also, for our definition of exponential function, we're going to assume that this base is not 0, because that would be boring. And we're going to assume that the base is positive. In other words, it's not negative. If it was negative, then it wouldn't be a continuous function. It wouldn't be very nice or very interesting. So instead, we're going to choose a positive base and a variable exponent. So when we get that, every exponential function becomes 1-to-1. If you've got 10 raised to the power x, this is strictly increasing. And it's continuous. And if it's strictly increasing and it's continuous, it's monotone, it's a 1-to-1 function. Every input maps to only one output. And you remember every 1-to-1 function has an inverse function. And what's the inverse function for an exponential function? This is the definition of what we call a logarithm, or a logarithmic function. A logarithm is just the inverse of an exponent. So if you were to see this, the way you read this out loud is you say the logarithm base 10 of x. And the logarithm base 10 is the inverse of the exponent base 10. So these two functions are inverse functions. The exponent base 10 is the inverse of the logarithm base 10 and vice versa. And then, because every exponential function is 1-to-1, this one has an inverse function too. See that inverse there as well. If I were to ask you, like in the first exercise of the homework, to find an inverse function, then this is what you do. We would say this function looks like y equals 1 minus 5 raised to the power x plus 3. And then I would want to change the y into an x. And change every x into a y. Just like that. And now I want to solve for y. So in order to solve for y, I would think to add 5 raised to the power y plus 3 to both sides. And then again, solving for y, subtract x from both sides. Now, how do I get rid of the exponent base 5? I could compose this with its inverse function. So I'm going to take the logarithm base 5 of the exponent base 5 of y plus 3. And to keep my equation balanced, I have to do the same thing to both sides. And it's going to look like this. Now, the reason I want to do this is because on the left side of the equation, when I compose the logarithm base 5 with the exponent base 5, they cancel out because they're inverse functions. And so the left side of the equation simplifies to y plus 3. Yeah, very good. And now, my inverse function is just perfect. So it's the logarithm base 5 of 1 minus x minus 3. So everything is just like we did in section 4.5. We changed the y into an x and the x into a y right here. That's the first step if you want to find an inverse, is you swap x and y. And then the rest of this is solve for y. That was the second step in finding an inverse. And the only new part about this is here. This is the only new thing today, is that if I take the logarithm base 5 of the exponent base 5, inverse functions, they cancel out when you compose two inverse functions. So that's the trick to solving. Okay, here's another example. This time my function looks like y equals 2 times logarithm base 3 of x plus 7 minus 6. And I'm going to make the y into an x and the x into a y. And now I want to solve for y. What do I do first? Add 6 to both sides. And then? Divide both sides by 2. And then? How do I get rid of the logarithm base 3? Yeah. So I need to compose with the inverse function. And the inverse function of the logarithm base 3 is the exponent base 3. And if I do the same thing to both sides of my equation, then it remains balanced. But the left side is going to become 3 raised to the power 1/2 x plus 3. And the right side is going to become 3 raised to the power logarithm base 3 of y plus 7. The reason I want to do this is because when I compose two inverse functions, like the exponent base 3 and the logarithm base 3, they cancel out and I get y plus 7. So that's the new part. If that's still not clicking, I'll try to write a short little explanation here. Because this is something we discussed at length in section 4.5. We said if we compose a function with its inverse function, then we should just get x when we're done, right? And so now we're saying, what if I have the inverse function of a function of y plus 7? Well, that should just be y plus 7. Again, because the exponent base 3 is the inverse function of the logarithm base 3. And this is what it looks like to compose that way. And so now, to solve for g inverse of x, I just have to subtract 7 from both sides. There we go. Questions? Okay. So, if I were working your homework, I would want to check my answer and make sure I did everything correctly. And one way I could check my answers is Desmos. I could type in what I had originally, which was 2 times logarithm base 3 of x plus 7 minus 6, I think. Yeah. And then I would type in 3 raised to the power 1/2 x plus 3 minus 7. And what we had discussed way back in the day in section 4.5 is we said, if I graph a function and its inverse function together on the same xy plane, then the curves should be a perfect mirror image of each other across the line y equals x. So there in green, that's my diagonal line y equals x. Is the blue curve a perfect mirror image of the red curve? Yeah. And so this is how you check your work. This is how you make sure, okay, that looks right, I didn't make any mistakes, and I can move on. If you get curves that don't look like that, then you've got to go back and find your mistake before you move on. So here we go. If I want to graph this function by making a table of values, I would set it up like this and maybe choose some values for x. If I'm dealing with the function y equals 2 to the power x, and I say x is equal to 1, then y is equal to 2. What if x is 2? Y would be 4. What if x is 3? Y would be 8. And if x is 4? Y would be 16. 2 to the 4th power is 16. So, we notice the pattern is every time I add 1 to my x value, my y value is multiplied by 2. So one way I could think about this pattern, and if I want to continue filling in values in my table, I might ask, is there a number where I add 1 and I get the number 1? What goes right here? So the question is, something plus 1 equals 1? 0. Yeah, that's what I was looking for. 0 plus 1 equals 1. And then what times 2 gives me 2? 1. There we go. And if I want to move another step backwards, then the question becomes, what number plus 1 equals 0? Negative 1. And then what number times 2 gives me 1? Something times 2 equals 1. A half. Yeah, 1/2 times 2 equals 1. And something plus 1 gives me negative 1, negative 2, and then something times 2 gives me a half. A quarter. Okay, and you can keep going in both directions like this here, but this might be good enough. So I'll start plotting these things, like when x is equal to 0, y is 1, when x is equal to 1, y is 2, when x is equal to 2, y is 4, x is equal to 3, and y is equal to 8, and then it goes off the chart. Like that. On the other side, when x is negative 1, y would be 1/2, and when x is equal to negative 2, y would be 1/4. When x is equal to negative 3, y would be 1/8, and when x is equal to negative 4, y would be 1/16. This kind of matches up with something we talked about at the very beginning of the semester. When we were talking about rational numbers, it was like section 1.2, is that if you have a negative exponent, it's just the reciprocal, right? So x being negative 3 is just the reciprocal of 8. That's 1/8. And so as I keep going off to the left, I'm going to get very, 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 very close to 0, but I'll never get to 0. It's always going to be 1 divided by a bigger and bigger number. It's never exactly 0. It just gets really close. So that's how you graph it. The slightly trickier question is, what if I wanted to graph this function using the table of values? And the trick is, I'm not going to make a table of values for logarithm base 2. Instead, I'm going to say, well, the inverse function of the logarithm base 2 is the exponent base 2. And I'm not going to make you do this again, because we just, a moment ago, in the last example, we made a table of values for 2 to the power x. It looked like that. So what's the trick? All I have to do is swap the x and the y. So here's what I mean. Take your eraser and scratch out the x and the y on your table, and then write y and x. Right? That's all you do to get the inverse function, is you just swap the x and the y. So now I go back and I say, all right, when y is negative 3, x is 1/8. And when y is negative 2, x is 1/4. And when y is negative 1, x is 1/2. And when y is 0, x is 1. And when y is 1, x is 2. And when y is 2, x is 4. And when y is 3, x is 8. Now I connect these dots. And this is a very nice curve representing my logarithm base 2 function. So instead of trying to make a table of values for the logarithm, you could just find the inverse, then make a table of values for your inverse, and then swap the x and y as your column headers on your table of values, and then plot those points. All right, slightly more complicated, but still not too bad, I think. I've got a new function. It's an exponential function, and I want to make a table of values and graph it. So maybe I start with x equals 2. If x equals 2, y would be equal to... Very good. Y is negative 2. What if x is 3? And if x is 4? Yep. And if x was 5, it would be 12. Okay. So I can stop, because that's going to be off the chart already anyways. What if x is 1? Negative 3? Yeah, because 1 minus 1 is 0, and you'll remember that anything raised to the power 0 is 1. And then if x is equal to 0, yeah. Because that would be 2 raised to the power 0 minus 1. So the reciprocal of 2 is 1/2, and 1/2 minus 4 is negative 3/2. You also have a calculator on your test. Like, you could be plugging these values into your calculator if you want to. And we can keep doing this if you want, but that should be enough, I think. So x is negative 1, y is negative 3.75, and I'll put down some of these dots. 2 and negative 2, 3 and 0, 4 and 4, and then we connect the dots. Okay, if we did this correctly, this should look just like the curve we graphed for 2 to the power x, but it should be moved 1 unit to the right and 4 units down. Remember section 4.4 when we talked about graphing the transformations and moving them to the left and right and up and down and everything else? So that looks exactly like the curve we had before, but moved to the right 1 unit and down 4 units. If I get something more complicated, like graph this function, again, this is a logarithm function, and I don't want to make a table of values for a logarithm. Instead, I'm going to find the inverse function. And the inverse function means I change the x into a y and the y into an x. And then I solve for y. So x minus 5 equals log 2 of y plus 3. What do I do next in order to solve for y? I need to get rid of the logarithm base 2 in order to solve for y. Yeah. I need to compose the exponent base 2 with both sides of this function. Because on the right side, when I do the exponent base 2 of the logarithm base 2 of y plus 3, that's going to simplify to y plus 3. And then lastly, to solve for y, I subtract 3. Like that. And now let's make a table of values for the inverse function, the exponential. And looking at this, I see x minus 5, so maybe I'll start with 6. And that way I've got 2 to the 1 power. 2 to the 1 power minus 3 would be negative 1. If x is 7, this becomes 1. And if x is 8, and if x is equal to 9, yep. So now I'm off the chart. What if I go back and say x is equal to 5? Negative 2. What if x is equal to 4? We got negative 2.5, 2.75, and so on. Yeah. All right, that's probably good enough. And if you have your calculator handy on your test, your TI-30 X2F, you could always make more points if you want to. But I'm going to start graphing and say, oh, ooh, what am I doing wrong? Yeah. Right now I'm about to graph this exponential function, but that's not what my problem is asking for. My problem is asking for the graph of the logarithm. So I have to change the x into a y and the y into an x. There we go. So now when y is 3, x is negative 2.75. When y is 4, x is negative 2.5. X is 5. Y is 5, x is negative 2. Y is 6. X is negative 1. 7 and 1. 8 and 5 and 9 and 13. So here we go. I'm trying to draw as close to vertical as I can. You know, every logarithm is going to have this singularity where it just shoots off down to negative infinity at some point, and it's not defined on the left side. But that's how you do this problem. Okay. To make it easier, we could do some of these problems where I've given you this function f, and now I want to plot a new function, g. What's the first step I should do if I want to plot this g function? Okay, because of the negative x, what's that going to do to it? It's going to reflect across which axis? It's either the x or the y axis, that's right. This time, if you've got a minus sign in the argument, that reflects across the y-axis. If you've got a minus sign out in front of the function, that's going to reflect across the x-axis. So there's a difference between 3 to the negative x and negative 3 to the x. And in this case, we're going to take every point along this red curve and make a little mirror image dot on the other side of the y-axis. And try to make that mirror image happen. Something like that. Okay, and then now if I want to get to my g function, you move down 6. So every single point gets moved down 6. And it's going to look like this. Remember, the order matters. The first thing you worry about is, am I moving to the left or to the right? In this case, no. The second thing you worry about is, am I going to stretch or squish or reflect this? In this case, yeah, that's what we did next. And then the last thing you do is move it up or down. So you can actually get the wrong answer if you do this out of order. But that's how you do it. Same thing with logarithms, but this time I've already given you the f function. And so really this is a question only about transformations. It doesn't really have anything to do with exponents or logarithms. You can do this with anything. What's the first step if I wanted to make this g curve happen? So I would swap x and y if I wanted to take the inverse function, but I'm not really worried about taking the inverse. I just want to graph the g function using transformations. Like I want to start with the f and then move it left and right, move it up and down, reflect it, stretch it, squish it. I'm not going to move it left or right because I'm not adding or subtracting anything from the argument here. I'm going to reflect it because I see this minus sign. Do I reflect across the x-axis or the y-axis? Yeah. If the minus sign is way out in front of the function, that's when we reflect across the x-axis. And this is my best attempt here. And then the last thing I do in order to get my function negative log base 3 of x plus 4 is I need to move every point up 4 units. 1, 2, 3, 4. 4. So these questions are exactly like the questions you saw in section 4.4. We're just graphing using transformations. Okay, these are tough. And it's easy to forget the definitions. So if I ask you for the domain of a function, the domain is the set of all x values that you can plug into this function for x. And still, whenever you calculate the function, you simplifying everything, you get a real number output. That's the goal for the domain. The range is the set of all possible output values. So that means if you take a function and you plug in every single number in its domain, what are the possible outputs that you're going to get out of the function? So if I've got the function 3 to the power x, what is my domain? What is the set of all x values I can plug in here and evaluate and still get a real number output? Yep. So all real numbers, everything from negative infinity to positive infinity, all real numbers are good. You can plug in positive numbers for x, 0 for x, that's fine. 3 to the 0 power is still 1. You can plug in a negative number for x and you just take the reciprocal. It's still good. It's still a real number output. So the domain is any real number you want to plug in. What is the range of 3 to the x? What numbers can I get when I take 3 raised to the power of some real number? Yeah. The range has to be greater than 0. Because no matter what I do, if I raise 3 to the 0 power, I get 1. If I raise 3 to a negative power, I get numbers between 0 and 1. But I can't ever get 0 when I do 3 raised to some power. Also, there's no way for me to get negative numbers, right? 3 raised to anything is still never going to give me a negative number. So the range is only the set of numbers between 0 and positive infinity. In the next question, with 2 raised to the power x minus 1 minus 4, what's the domain of this function? Yeah, it's the same thing. So the domain is asking what numbers are you allowed to plug in for x? And just like before, I can plug in any real number for x, and 2 raised to any real number is still going to be a real number, so I'm good. I don't have to worry about restricting the domain because I can do anything for my x value. What's the range this time? This is how I think about it. I look at the first term where I've got 2 to the power all real numbers, and I think, well, the range of that has to be 0 to plus infinity, right? 2 raised to a real number, it can't be 0, it can be negative. So that's my range of that first term only. What does the minus 4 do to my range, though? Yeah. So if I move this interval down 4, then 0 minus 4 is negative 4, and infinity minus 4 is, yeah, it's still infinity. And again, to check your answers on your homework, like, what do you do? This is the graph, right? Again, the domain is what are all the x coordinates I can get to with this curve? And clearly this curve goes on forever in the negative direction, and it gets really steep, but it does go on forever in the positive direction, right? You can always take 2 to a larger and larger positive number. What about the y coordinates? What kind of y coordinates can I get to with this curve? Well, I can get to all positive y coordinates if I scroll up, but there is a lower bound on the kind of y coordinates I can get to. This purple curve never goes below negative 4. It stops there. So we say the range is everything from negative 4 up to positive infinity. The range is the y values. Okay. This is a little tricky. this time my function is 5 raised to the power -1 over x plus 2 minus 4. Okay, so the function 5 raised to the x minus 4, that would have every real number in the domain. So -1 over x plus 2, it could be any real number. But is there any values of x that I cannot plug into this function? -2. I'm going to write my domain like this. Because that way it reminds me I cannot have -2 in my domain. If I tried to plug in -2, I would get -1 divided by 0. And that's not a number. It's not defined. We don't get to calculate that. Okay. For my range, this is a tricky question. This is my line of reasoning with the range question. I say, first of all, -1 over x plus 2 can never reach there's one number I can never get to, no matter what I choose for x. I could make this reach -2 if I made this x equals -1.5, right? X equals -1.5 plus 2 would be a half, and -1 divided by half would be -2. But this value, no matter what I choose for x, this value can never ever be 0. Yeah. I'm always going to have -1 divided by something. I can't ever make that into a 0. And so if this can never reach 0, then 5 raised to the power of something that can never reach 0 what's 5 to the 0 power? 1. So this part, the first term in my function, can never reach the number 1. And then that means my f function can never reach 1 minus 4. -3. So for my range, I can get to all of the numbers except for -3. Okay, so I say this probably enough times. If I want to check my answer, it's 5 to the power -1 over x plus 2 minus 4. Oh. Maybe this is a lot more interesting than I thought it was. Is it though? So I got my domain, right? Like my domain includes all the x values except for -2. You see where the discontinuity here is at -2. But what's wrong with the range? It looks like the range starts at -4. It's I guess because 5 to the power -1 over x plus 2 can never reach 5 to 0 equals 1. That's true. And also, this is positive, right? 5 to the power anything is greater than 0. It's an exponential function. And so that means my range, if this is a positive number -4, then my range has to start at -4. So let me say that one more time. The first term here has to be a positive number because you've got 5 raised to something, right? And so we talked about exponential functions. They always have a positive range. So I've got something that's positive, -4. Well, the lowest you can get to is -4. So this is my real range with my mistake corrected. All right. A few more examples. Now we're switching gears and we're doing logarithm domain and range questions. Here's the domain and range of the logarithm base 3 of x. And to remind you really quick, what did we say was the domain of 3 to the x? The domain for an exponential like this is all real numbers, and the range for an exponential was like this. So now if I ask you, what's the domain of my logarithm? What's the range of my logarithm? What do I do to find the domain and range of my logarithm base 3? Yeah. I'll just swap the domain and range, because these are inverse functions. And the domain of the inverse function is the same thing as the range of my original function. And likewise, the range of my inverse function is just the domain of my original function. Easy. In my next example, I would solve this by first finding the inverse function and then solving for y, right? Swap the x and the y and then solve for y. So this would be 2 to the x equals y plus 5, or y equals 2 to the x minus 5. So the inverse function, this f inverse, that has a domain of all real numbers, because it's an exponential function. And that, can accept any number in the domain. The range, however, would be, -5 to infinity. And that's not what my question was asking, though. My question was asking about the logarithm. And so for the logarithm, the domain is going to be -5 to infinity. And the range will be
infinity.
Just swap the domain and range for the inverse. Cool. One more, and this is a fantastic question. Before I do this question, I just want to tell you this. Whenever I have a logarithm, like this one, and it doesn't even matter, the logarithm base anything of x has a domain of only positive real numbers, right? What I'm trying to tell you is that if you tried to take the logarithm base 5 of 0 that's not defined. You can't take the logarithm of 0. And you can't take the logarithm of any negative number. Okay? It's just not in the domain of the logarithm because it's not in the range of the exponential function. That's always true. So I can't take a log of 0. I can't take a log of a negative number. And what that means here, when I ask for the domain of the function logarithm of x plus 4 over x minus 2, well, I know x plus 4 over x minus 2 must be greater than 0. Because if that is equal to 0, I can't take the logarithm of 0. And if it were less than 0, well, I can't take the logarithm of a negative number. So this has to be true. It has to be positive. Since I'm dividing here, there's two ways that this could happen. Number one, I can get a positive number if I take a positive number divided by a positive number. That means if x is greater than 2, I'll get something greater than 6 divided by something greater than 0, so a positive over a positive, and that works. Another way I can make this happen is if I have a negative number divided by a negative number. I can make that situation happen if x is less than if x is less than negative 4. So the problem is if x were somewhere between negative 4 and 2, I might end up with a positive number divided by a negative number. And if I have positive divided by negative, then the whole thing is going to be negative, and I can't take the logarithm of a negative. So one of these has to be true. Either x is greater than 2 or x is less than negative 4. If either one of those are true, then my argument is positive and I can take the logarithm. So all told, my domain is going to look like this. The first interval is the interval of numbers where x is less than negative 4, and then union with the second interval where x is greater than 2. And then we ask, okay, what about my range? The range is no less tricky. This function, x plus 4 over x minus 2, this is a rational function. It's got one pole, and it's got 1 0, and I guess what I'm trying to say is that this is the same thing as 1 plus 6 over x minus 2. Did I do that right? The x minus 2 plus 6. Yeah. Right, so the left side is an expanded form, the right side is just a mixed form. And this can never reach what number? You're right that I can't plug in 2, right? Because 2 minus 2 is 0. I can't divide by 0. But what I mean is, like, if I plug in any x value in my domain, then this 1 plus 6 over x minus 2, the whole thing that could never be the number 1. The reason is because 6 divided by something could never ever be 0. And so if I have 1 plus something that's never ever 0, then it can never be 1. Okay, that can never be 1. And so that means f can never reach the logarithm of 1. Do you know what the logarithm of 1 is? So let's find out what the logarithm of 1 is. Let me say z is equal to the logarithm base 3 of 1. If I said 3 raised to the power z is equal to 3 to the power logarithm base 3 of 1, this cancels out, right? 3 to the power log 3. So z is the number for which 3 raised to the power z is equal to 1. So what does z have to be? 0. Yeah, anything raised to the power 0 is just the number 1. So z has to be 0, and that means the logarithm base 3 of 1 is equal to 0. And so my f function can never reach 0. And what does that look like? Well, normally the range of my logarithm is all real numbers, everything from negative infinity to positive infinity. Only the issue this time is I can never reach 0. So let's check our work really quick and see how this goes. That's my function. And what I claimed to say about the domain is that the domain couldn't have any x values that were between -4 and 2. These are places where this purple curve just does not exist. And then the other thing I said about my range is that the range could be any real number, it just can't ever reach 0. And that seems to be the case here too. So that's how you check your answers. That's a pretty tough problem. This is a problem so hard that maybe on the test I would give you the picture. I'll give you a picture of the graph as well as the formula so that you can use both to reason about getting the correct answer. If it's an easier domain and range question, maybe I only give you the formula or I only give you the picture. If it's a hard domain and range question, maybe I give you both. Okay? Y'all have a good day, and we'll see y'all on Wednesday.